Hello there. Today we'll be finishing up the DP problems. We'll be completing longest increasing subsequence. When you think about increasing subsequence, you're thinking of like this. So in this particular item, the longest increasing subsequence is 2, 3, 7, and 101. So as long as it's increasing, it is going to remain. It's going to keep on increasing. You can check every other number to see if it's increasing. So this is 2, 5, and you look for 7, and you look for 101. One way to do this is to do backtracking and look through every single number. What does that mean? That means what you're doing here is you're looking at the, let's say 0, 1, 0, 3, 2, 3, and you are taking, let's say, a 0 or not a 0. Then you're taking a 0, 1, a 1, or well, 1 or nothing at all, and you keep taking these numbers and you find out if any of these are increasing subsequences. One way to make this faster is to say, oh, if it's no longer increasing, we can stop looking. But a better way to do this is to do this with a dynamic programming. And one thing we can see with increasing subsequences are that if you look through backwards, so this would be a 1, right? So let's say here this is a 1. And if you look at the previous item, when you take a look at this item, and you look at the next item in front of it, if it is 1, then this must be 2 if it's less than this number. For this number, well, it can be either itself, which is 1, or if it's smaller than this number, it'll take this number and add it on. And if it's smaller, then it'll take this number and add it on, but it's not, so it's 1. So our formula here is going to be we're going to take every item here and read every other item to find the maximum item to see if we can make that bigger. So of course we take 0 and 3, that's 2. That's 2 items, 1 or 2, 2 items. Then we take 0, 2, and then look at that number and we see a 3. And we take 0 and then say 0, 2, 3. 3 is a 0 and 3 is 1, so that would be 2. But we take the max, so that would remain as 3. Then we would take a look at 1 and we check every single item. If it's less than that item, then we'll tack 1 onto that. So we have 1, 2, and 3, so that's a 3 again. And the last one, we check this number and we check all of these numbers here. And by checking that, we see that we are smaller than 1, and so we can get a 4. And so we will return 4 as suggested here in the example. So how will we do that? We can do this top down or bottom up. Let's do this top down first, and then we'll do this bottom up. So so to do top down, we need a DP, and we set all the items to 1 because every number is item 1. And we're gonna go for the range, I in range of length nums minus 1, and negative 1. So that means we're gonna go backwards as we have suggested. Oh wait, that's bottom up. My bad. Let's just block that out for now. And so we're gonna run DFS of I, and if I is equal to the length, that's our base case, we're going to return 1. Otherwise, we're going to do 4. We're going to run DFS for I plus 1, and for j in range of I plus 1, so every item, all the way until length of numbers. And then what happens is that we check if the numbers of I is less than the nums of j. What we're gonna do is get dp of I is gonna be equal to the max of dp of I, the current number, or it's gonna be dp of I think j 1 plus j. So we get one more than that, and with that we would have our dp, and we would return our dp of I, our biggest number at that particular point. Yeah. So let's run it. So let's return So let's run DFS of 0. So we look at this. We want to know all the numbers, and we're going to return the max of DP, because DP doesn't necessarily have to be at 0. It can be anywhere in the dynamic programming. Our store of cache. So let's print it out, see what's going on. Print DP of I. Run code. And oops, my bad. I should just print DP. Okay, start at 1. We move to 2. Okay, let's work on this one, which we've done an example of. So we had 1, 1, 1 originally, and we have 2. Then we have 1, 1, 3, 1, 3, and then 4, as we have talked about earlier. So this should work pretty well. Let's submit it. Okay, so with that, we have done the top-down method. Let's do the bottom-up method now. So the bottom-up method is basically the same, but instead of starting at 0, we're starting at the end, so we don't have to go all the way down and go back up. So we start with the same, like, what do you call this, DP, to hold the numbers. So for j in range, I plus 1, so all the numbers pass I, all the way to the length of nums. And for each of that, if nums I is less than nums j, that means there's a shot. We can tack this on and see if this is going to make us the longest item or not the longest item. And we want to keep the longest item so that when we see that number, if it's smaller, we can tack that on. So return max DP. Let's run. And let's submit. So to make this a top down, and we need to write bottom up. So these are not the fastest solutions out there. This is n squared time. There is a way to get this in n log n, I hear, but I don't think that's too important for an interview. It might be fun to invest your time into and take a look. But I think this is plenty of learning about how to look at the pattern of increasing subsequences, and how having a bigger number means that it would reset to a 1, or you can take any number that is smaller. If your number is smaller than any number above it, you can take that number's the number of times you've seen it. That can be attached to another number and tack a 1 on top of that to extend the subsequence. A way to remember that information, at how many items are possible at that particular index. So I think that's enough for this problem. Hopefully when we come back for this problem, we might learn something even more. But right now, this is what we've learned, and I hope to see you in the next video. What else? Yes, if you enjoyed the video, like and subscribe. If you want more content, check the link in the description below. Thank you very much, and I'll see you in the next one.